Right, let's do some physics. There's an exam paper here, foundation tier, paper 1. Waves on the surface of water are transverse waves. State one other example. So I'll just go for light. Sound waves are longitudinal waves. State one other example of a longitudinal wave. You can have a P wave, which is a seismic wave, it's an earthquake wave. You could have ultrasound, you could have infrasound. The graph shows a water wave. Complete the sentence by putting a cross in the box next to your answer. The amplitude of the wave is, well, the amplitude is from the middle to the top. So in this case that's 24. Each box is worth 2. So the answer is C. The diagram shows a ray of light incident on a boundary between air and glass. This becomes 2 rays P and Q. Use words from the box to complete the labels in the on the diagram. Incident, magnified, normal, reflected, refracted. Well, this ray here is being reflected because it's bouncing off. Because it's bouncing off a surface. And this ray here, Q, that's been refracted. It's been bent. A sound wave in a solid has a frequency of 1100 Hz. The wavelength of this wave is 3 meters. Calculate the speed. So wave speed equals frequency times by wavelength. So that will be 1100 Hz multiplied by 3 meters, and that's 3,300 meters per second. So the unit is meters per second, and the answer is 3,300. Question 2. A. Which row of the table is correct for a seismic S wave? Put a cross in the box next to your answer. Is a seismic S wave electromagnetic? No. So it's either A or D is correct. Is it transverse? Yes it is. So the answer is D. Complete the sentence by putting a cross in the box next to your answer. Earthquakes occur between a plate in the crust and a second plate in the crust. So the first one's right. So when the tectonic plates rub together. C. The diagram shows circles drawn around 2 earthquake monitoring stations. The circles indicate the distances of an earthquake from each station. Explain why this is not enough to locate exactly the position of an earthquake. So the position of the earthquake could be anywhere where the circles intersect. So it could be here or here. What we need is a third circle. Perhaps the third circle would be there like that. Not much of a circle, mind. And then you'd be able to tell that the earthquake came from here. If you put another circle on and it came up here, then obviously that would be where the earthquake was. So circles intersect at 2 places. Earthquake could be at either of these places. We need a third circle or monitoring station. The diagram shows the different traces that the same earthquake produces in seismometers at 3 different towns, TU and V. Suggest two pieces of evidence that show that towns are at different distances from where the earthquake happened. Well, you can see town T has received the signal at 20 seconds, and U has received the signal at 25, and V has received it at 30. So the towns have received the signal at different times. Towns received the signal at different times. And also, the further an earthquake travels, the less energy it has. So you can see here, this earthquake has got loads of energy by the time it hits town T. It's lost a little bit of energy as it hits U, and it's lost even more energy as it hits town V. So the amplitude, how far up and down the wave goes, is called the amplitude. That's the energy. The amplitude or strength of the earthquake has decreased from town T to U to V. E. Explain why scientists find it difficult to predict when a tsunami wave will occur. So a tsunami is a massive wave, and it's caused by an undersea earthquake. You can't predict when an earthquake will happen, so you can't predict when a tsunami wave will happen either. Tsunami caused by earthquake. You can't predict when an earthquake will happen. Number 3. Complete the sentence by putting a cross in the box next to your answer. The unit of potential difference is that'll be the volt. Amps are for current, joules are for energy, and watts are for power. Part B. Choose words from the box to complete the sentence. Electrical energy is transmitted at high voltages because it improves the efficiency by reducing heat loss in the transmission lines. C. When a voltage of 12 volts is applied to the input coil of a transformer, there is a current of 0.5 amps in the output. Calculate the input power of the transformer. Right, so power equals voltage times by current. So that equals 12 volts times by 0.5 amps. And that equals 6 watts, if you're clever. Question 3D. The student investigates induced voltage. She pushes a magnet into a coil at different speeds. She puts some of her results on a graph. When the speed of the magnet is 6 centimeters per second, the induced voltage is 4 millivolts. Plot that on the graph with an X. So 6 centimeters per second will be there, and 4 millivolts will be there. Draw a line of best fit. Complete the sentence by putting a cross in the box. When the speed of the magnet is 20, the induced voltage is about, so go along to 20 centimeters per second. The induced voltage is about 14. So 13, 14. There's 13, it's the closest one. Number 4. The table gives some information about the Earth and about Pluto. Calculate the shortest distance between Earth and Pluto. So, distance from the Sun, well, if that's the Sun there, and let's just say that the Earth is there, which is 15, and Pluto's right over here, 591. So if you want to know the distance between the Earth and Pluto, then we need this distance here. So if you do 591, take away 15, that'll give you your answer. That's 576. In fact, the distance between the Earth and Pluto is always changing. Explain why the distance between the Earth and Pluto is always changing. You may draw a diagram to help your answer. Right, well, there's the Sun, there's the Earth, there's Pluto. So you can see the distance there is that much, whatever that is. Now, because the Earth is closer, so P for Pluto, E for Earth, S for the Sun. Because the Earth is closer to the Sun, it's orbiting faster. So in the same amount of time, Pluto might have just went to there. So now you can see the distance is much bigger than it was. So Earth orbits faster than Pluto. Earth orbits the Sun faster than Pluto. So positions of Earth and Pluto relative to each other change. Light takes 8 minutes to get from the Sun to the Earth. Calculate the time it takes for light to get from the Sun to Pluto. Well, you can see Pluto's a lot further. How much further? Well, how many times does 15 fit into 591? So if you do 591 divided by 15, so that equals 39.4. So that's how many times further Pluto is from the Sun compared to the Earth from the Sun. So if it takes 8 minutes to travel 15 units, it's going to take 8 minutes times by 39.4. It's going to take 39.4 times longer in time to travel 39.4 times longer in distance. So that's going to be 315.2. So 315 minutes. The Sun is our nearest star. Use words from the box to complete the following sentences. Our Sun was formed from a collapsing nebula. It's just a massive ball of dust and gas. The next stage in the evolution of our Sun will be red giant. Our Sun's just classed as quite a small star, so when it burns off its hydrogen, it'll turn into a red giant. Our Sun will end up as a white dwarf. It'll then turn into a black dwarf, but that's not an option. Visible light and microwaves are both electromagnetic waves. Complete the sentence by putting a cross in the box next to your answer. Electromagnetic waves all have the same wavelength in a vacuum? Nope. Some of them are longer, some of them are shorter. It doesn't matter where they are, whether they're in a vacuum or not. All have the same wavelength in glass? Nope. All travel at the same speed in a vacuum? Correct. All travel at the same speed in glass? Nope. Part 2. Visible light can be split into colours. The diagram shows the colours arranged in order of frequency. Complete the diagram by writing in the four missing colours. Richard of York gave battle in vain. Red, orange, yellow, green, blue, indigo, violet. Microwaves have many uses. State 2 uses for microwaves. Cooking me beans and communicating with satellites. There we are. B. The potential danger of electromagnetic waves increases as the frequency of the waves increase. Compare the harmful effects of 2 types of electromagnetic waves on people. Choose one wave with a lower frequency than visible light and one wave with a higher frequency than visible light. So if we quickly whip up the electromagnetic spectrum. Visible light's in the middle, which is Richard of York gave battle in vain. R for red, for infrared, V for violet, for ultraviolet, R for red, R for radio, which is the longest of the waves. The shortest of the waves is over here, gamma. Next to that is a wave which is pretty short as well, X-rays, and that just leaves microwaves over here. So one wave with a lower frequency, so over here the waves are long, and as you start getting over here, the waves have got much more energy and much more higher frequency. So choose a wave with a lower frequency than visible light. So it's any of these bad boys. Harmful effects. Well, microwaves, internal damage to cells, AKA they'll cook you. Infrared, well that's just heat, so that can burn you. Radio's the safest of all the waves, so I wouldn't pick that one. Choose one wave with a higher frequency than visible light. Any of these. UV, that could cause your skin cancer. X-rays damages your cells, could cause cancer. Gamma rays damages your cells, could cause cancer. So the answer over here is cancer. That's an easy one to remember then. A student has a battery powered torch. When the lamp in the torch is lit for 10 seconds, 9 joules of energy is transferred in a useful way and 61 joules is wasted. Complete the table to show the amount of energy each form. Right, well, what do you want from a torch? You want light, so that's the useful. So 9 joules of energy is transferred in a useful way. 61 joules is wasted. Bulbs get hot, so that's thermal energy, that's the wasted energy. And electrical energy powers the whole thing, so you must have lobbed that in at the start. So 61 plus 9 is 70. Soon after the torch is switched on, the temperature of the filament in the lamp reaches a steady high temperature. The filament stays at this high temperature even though electricity is still being supplied to it. Explain why the temperature of the filament in the lamp remains the same. Well, the energy that it's gaining must be the same as the energy that it's losing, so the temperature remains constant. Energy gained equals energy lost, therefore temperature is constant. B. The energy supplied to a machine is 2,500 joules. The machine is 20% efficient. The equation for finding the useful energy transferred by a machine is that useful energy transferred by a machine is the total energy supplied to the machine multiplied by the efficiency of the machine divided by 100. Calculate the useful energy transferred by this machine. So the total energy in was 2,500 and the efficiency is 20%. Divide that bad boy by 100 and that equals 500 joules. Question C. A student investigates the energy chains for a 60 watt lamp and a 15 watt lamp. The diagram shows the energy chains for each lamp. Each energy chain starts with the amount of energy supplied to the power station, that's this over here, in 1 second, and ends with the light given out by the lamps in 1 second. Oh, look at that. So they both give out 1.5 joules of energy. Some of the energy supplied is wasted in the chains. So where's the actual question? One of the lamps is described as an energy saving lamp. Explain why using the energy saving lamp saves energy. Quote values from the diagram to help you with your answer, and that's worth 6. Right, let's go back up to here then. So this one needs a lot more energy than this one. They both get the same output energy. Same output energy, but 15 watt lamp had 188 to take away 47 joules, so that's 141 joules less input. Don't just quote the figures, manipulate them, right? Take one thing away from another thing and all that type of stuff. You can see here the 60 watt lamp wastes 58.5, whereas this one only wastes 13.5. 15 watt lamp wastes much less energy, so 58.5 take away 13.5, so that's 45 joules. In the transmission lines, 8 joules is wasted there, whereas only 2's there. So 15 watt lamp wastes less energy in transmission wires. So let's work it out. So wastes 6 joules less. And we may as well compare this thing here. So that's 30 joules there, and that wastes 120. 60 watt lamp wastes 90 joules more energy at the power station. So you can see at every part of its journey, the 60 watt lamp is wasting more energy. So the 15 watt lamp, that must be the energy saving lamp. There's a few blank pages, isn't there? Oh, is that it? Have we done it? Oh, we're finished. Oh well, that was easy. That was over quickly. Right. Well, I hope that helps you. Alright, cheers. Ta-ra.